The link budget is an important basis for all kinds of wireless systems. A structured and simple spreadsheet makes it easy to understand. In this episode, we will talk about a method that is very important in the wireless world. We need to talk about the so-called link budget. In my mind, it represents the best end-to-end view over any wireless system. It gives us a nice structure to separate and understand the elements that play a role. Furthermore, it will give us insights for the design of our own projects. And sometimes we need to convert units of measure to the ones we need. Our spreadsheet gives us a proper structure for the link budget as well as a unit conversion tool. In earlier episodes, we learned how to predict the wave propagation loss. The tools that we provided earlier are asking for the so-called effective isotropic radiated power as an input. The output that we get is the so-called effective isotropic received power and the propagation loss, which is the difference between both. These parameters both are defined outside our boxes, in the air, if you will. In other words, they are not measurable inside the technical wireless system that consists out of antennas, printed boards and cables. I really have to admit that the effective isotropic stuff appears a bit funny. The definitions are based on a theoretical model of thought with antennas which would radiate evenly in all directions. Such antennas do not really exist. However, this is the best way to understand and design wireless systems because it allows us to separate the problems that you need to solve in a wireless project. In addition, these values are often the basis for regulatory bodies to describe the limits of the transmit power. In this episode, we will derive the effective isotropic radiated and received power from the link budget. The bottom line of the link budget will be the so-called systems gain. A fundamental condition for a wireless connection is that the system gain is greater than the wave propagation loss. Now let's tackle the link budget and an example. As you know, we want to convey methods and knowledge through our channel. I think this works best by complementing the video with transparent tools. As a principle, I keep all formulas visible in my spreadsheets. The little spreadsheet here is a template for the link budget. We look at both directions, the uplink and the downlink. And we look at the transmitter and the receiver side for both directions. We work with logarithmic values in dB so that we just need to sum up to get the desired budgets. And yes, it is correct to add up dBs with dBms with dBis. Don't worry. As you can see from the table, intermediate results are the effective isotropic radiated power and the effective isotropic received power. The budget's bottom line is the maximum system gain that we can achieve. By the way, Experts are talking about a balanced link budget when the maximum system gain is equal for uplink and downlink. You guessed it, this is important that the system can work in both ways, uplink and downlink. Of course, there would be many ways of presenting this. However, I think this is the best method. It is well structured and understandable. Please note that in this sheet, loss is represented as a negative value, which appears then in red. Gain is positive and appears in black. Okay, now let's assume the following example. You know, I'm a fan of the LoRa technology because it is so interesting for hobbyists and it has a commercial growth potential in my mind. We assume a LoRa gateway with an outdoor antenna and a few meters feeder cable between the antenna and the gateway box. Somewhere outside in the field we have a compact LoRa IoT unit that is sending sensor data to the gateway, and it is receiving commands from the gateway, for instance to switch water on and off. Let's get to the details now. The used LoRa transceivers, both are specified with 18 dBm internal transmit power. We start from the uplink side, which is the left column. On the top line we insert the IoT unit's internal power. Before the internal power gets to the board's connector, it has to pass an onboard filter that is reducing the harmonics and the spurious emissions to the allowed level. The filter's transmission loss is 3 dB. We insert -3 here. This gives us then the board's actual output power of 15 dBm. The compact IoT unit has a short internal cabling and connectors for the antenna. We need to insert 2 dB's loss for the cables and the connectors. The antenna is a short helical antenna with 0 dBi gain. The result for the IoT unit's effective isotropic radiated power is 13 dBm. Next, we go ahead with the uplink on the receiver part. Our LoRa receiver sensitivity on the gateway side is -118 dBm. Several meters feeder cable together with the connector's loss adds up to 9 dB loss. We insert -9 here. The gateway's outdoor antenna has a gain of 8 dBi. That's why we insert +8 here. This gives us the receiver sensitivity of -117 dBm effective isotropic received power. The uplink maximum system gain is 130 dB. Next, let's go to the downlink side, which we have in the right column here. The internal power and the filter loss are the same as before because we use the same LoRa transceiver board for the gateway. We get the same output power of 15 dBm. Since we use the same antenna for sending and receiving, we insert also -9 dB for cable and connectors, as well as the +8 for the antenna gain. In the downlink we get +14 effective isotropic radiated power. We go ahead with the downlink in the receiver part. We insert the receiver sensitivity of -118 dBm. And again, since we use here the same antenna for transmitter and receiver, we have to insert -2 for the cable and connectors and 0 dBi for the antenna gain. And that's it. By the way, we can learn something interesting here. The link budget can be asymmetric. However, from the maximum system gain, we can see that it is still balanced. This is what professional radio engineers usually want to achieve, so that both directions can achieve a similar range. After that simple calculation, we get now the desired effective isotropic radiated power and the effective isotropic received power. This is on one hand important because we need to know whether our system is compliant with the law, and on the other hand we need it to predict our radio range. Of course, you can use the spreadsheet for any other wireless technology. You can roughly judge the potential range of any wireless system already from the calculated maximum system gain. You will find that, for instance, Wi-Fi has a far lower system gain, and for instance GPS has even a higher system gain than LoRa. In our episodes that are dealing with wireless technologies, we went through a number of questions that we tackled with some cool tools. What else could prevent us from a successful planning of our wireless projects? Well, sometimes we get specifications in other units of measure and we cannot directly use them in our tools. And when we were talking about field strengths in dBms, we were not 100% precise, because field strengths would be volts per meter or dB microvolts per meter. But we used it as an equivalent. Why could we do that? It is because for electromagnetic waves, the electrical field strengths, the magnetic field strengths, and the power flow are related. The relation depends from the so-called intrinsic impedance of the medium. In our case, the medium is usually just air, which has an impedance of 377 ohms. What? Yes, air has an impedance for electromagnetic waves. Actually, it is the impedance of free space in vacuum, and in air it is almost the same. Cool, isn't it? This is the reason why these values are all proportional. Well, sometimes nature is making it a bit easier for us. However, the conversion of the field strength from dB microvolts per meter to the effective isotropic received power and vice versa is a bit of a headache. But don't worry, here's the cure. Our little tool here is able to convert some of the most important units of measure which you will find in connection with electromagnetic fields. I will demonstrate some examples now. Say the field strength is specified to 25 microvolts per meter for a signal that you want to receive. Unfortunately, this is the only specification you got. How can we tackle this? Before we start, here is an important hint. For the conversion, you need to know the frequency. Let's carry out the conversion now. We insert the 25 microvolts per meter here, and we assume a signal at 868 MHz, which gives us then an effective isotropic received power of minus 110.98 dBm. Applying a good antenna, we could expect a stable reception for this field strength in the case of LoRa, because this is well above the receiver sensitivity. We could do the reverse conversion here in the middle section. In the section on the right side, we can calculate the magnetic field and the power flow from the known electric field under free space conditions. As an example, we inserted the electrical field that we calculated before. Just to complete the little conversion tool, we added at the bottom the conversion from power to power level in dBm and vice versa. For example, inserting the calculated minus 110.98 dBm yields about 8 femtowatt as a received power. The summary. We applied a structured method to calculate the link budget, which covers a whole wireless system end to end. The episode complements the earlier episodes that were dealing with wave propagation prediction. We learned how to calculate the so-called effective isotropic radiated power and the so-called effective isotropic received power from the hardware elements that we are using in our projects. Now we can understand the contribution for wave propagation of all elements end to end for any wireless system in both directions. As always, you can download the little spreadsheet as a reference for the method, or you can apply it to design your own projects. The past 3 episodes were covering methods and tools that you need to predict the range for a number of wireless systems. By applying the given tools, you're able to make your own essential calculations to choose an adequate wireless technology, the right antennas, the right sites, etc. Many of us know that antennas can make a big difference. I feel that it could be worth it to talk about some basic properties of antennas. The coming episode will cover antenna diagrams, gain, reflection loss, VSWR, etc. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.